Yeah, so for some announcements, so the check-in reports, which were like originally due today, are actually going to be due on Wednesday. You guys should be able to see like the B courses like assignment for that. And so as you guys know, also final project presentations are on the 26th and 28th. So that's next week. So definitely keep working on those. And so definitely like come to office hours if you need. Like there's office hours right after lecture today and like tomorrow and Wednesday and on Friday. So there's definitely like a lot of help if you need. Yeah, so today is the last week of lectures. And can someone link the attendance form in the chat?
Yeah, I got it. I just want to add the presentations are the 26th and the 28th, but your assignment will be due before the first day of that week. So 26th, it'll be due at 5 p.m. on the 26th, your final project. And I put out an announcement / assignment today, so you should be able to see it.
Okay, yeah. Okay, yeah, so today's Monday. And so we'll just get started with some like breakout rooms. Like today's like pretty chill lecture. We're just gonna be kind of doing an overview about like machine learning. But obviously that's like a really complicated topic. So just kind of showing some examples and like what are some applications of it. Yeah, so I'll open breakout rooms. You guys can just kind of talk about like how are our final projects going, like what types of libraries, methods, or data sets have you been using, and like what kind of problems are you guys running into, you know, just so you can kind of like talk about that. Yeah, there's actually like some fire trucks like right outside my building. I don't know if you guys can hear that, but yeah, let me assign some breakout rooms.
That's so tough. Raph, Kevin is saying, he's texted me, for 110A. That's not
what? Which one?
I think number 1.
Damn.
That's tough. Pretty sure I'm right though. He can just
okay. Yeah, we can figure it out later.
Yeah. Which machine learning application are you? I'm personally image recognition. That's me.
Yeah, I think that's a pretty cool one.
Yeah. I'm just gonna say it right now. I think Raph is stock market trading. I think that's definitely Raph. I want to say Isla is email spam and malware filtering.
Why?
No idea. It's just first thing that comes to my
I feel
mind.
like Isla could be some like automatic language translation.
Oh, I like that better.
You don't want to be email spam filtering? That sounds like useful. All right.
Okay, yeah. Okay, so I think everyone's out of the breakout rooms now. So does anyone want to like share like something you guys are talking about like related to your final projects? Just like how like a kind of status update or like anything that's going good or bad so far? Okay, we don't have to do that also, you know, just like if you guys want to talk. I hope you guys are talking in the breakout room though. Okay, so today we're going to be talking about like machine learning, and I feel like that's kind of like a word that's thrown around a lot and like no one really knows what it means, but like it's actually used in like a lot of things we use like on a daily basis. So like some kind of common examples are like, you know, self-driving cars. Like I know like Tesla's doing a lot of stuff with that where like the car can drive on the highway itself. And even just things like the recommendations you see on like Netflix and TikTok, like that's like a lot of machine learning because the computer kind of like takes all of the data of like posts you've liked, like movies you've watched to like recommend you other things. You also have things like speech recognition, like with Siri and Alexa. There's other like language things like Google Translate. even in like the medical field with like diagnosis using like x-rays, and also just like face recognition for when you like unlock your phone. Yeah, so let's like kind of step back and like take a look at what machine learning is. So basically, like I'm sure like a lot of you have seen from doing your final projects, like a lot of you are trying to simulate like galaxies and stuff like that. And like programming real life applications is obviously really difficult, just because in real life, like it's so hard to have an equation of things like what kind of movies someone likes. Like there's no equations to really describe that. And so oftentimes there's like too many factors to code. And so kind of the main idea behind machine learning is like, what if instead of coding everything ourselves, we let the computer learn through examples and training. So basically the CPU learns through experiences and rewards, kind of similar to how like a person would learn how to like ride a bike or something. Like they would go through some like training and like figure out like what works and what doesn't work. Okay, so in machine learning, there's kind of two main branches. There's supervised learning and unsupervised learning. And basically the difference is that in supervised learning, you're given data with like labels as well. And so this just means that like given data, like so your X values, your input values, there are also like Y values associated with them. And so this kind of includes like regression. And so like in this class, we've already seen like basic linear regression. And so technically like we have already kind of like learned some machine learning topics in this course, though like, yeah, I wouldn't say that like you're an expert or anything in the topic. Obviously like there's a lot more complicated things with like other models of regression and like figuring out how to like minimize your errors. And so also in the supervised category is classification. So things like, is this image a person or a car? And basically with classification, it's like taking data or maybe like images and being able to classify, like correctly classify what type of class this belongs to. Okay, and then with unsupervised learning, this basically gives, like as we were seeing before, like X input data, like X values, and the machine will create the labels itself. So like this is really useful if you're not totally sure what kind of patterns there are. Like the computer will kind of cluster things and like group things. So like by common patterns. So you don't have to necessarily input anything yourself. And so if clustering, an example is like Netflix classifying movies as like irreverent thrillers, like a lot of times you'll notice that the categories are really random. And it's because like they're not really created by humans. It's just created by like an algorithm. So it just takes common words that like movies share. And so that's why a lot of times the topics can be really specific and kind of random. Yeah. Okay, so with regression, we've already seen like linear regression, but there's also a lot of other types of models like polynomial or logistic regression. Logistic regression isn't really relevant to this course, but it's like more used for like probability like out of 1. And so basically in regression, the basic idea is like you want to calculate the parameters that minimize the error given your input data X and labels Y. And so in general, real data is never perfect, and so there will always be errors. And in general, you want to find like the parameters that best minimize these. And it's also really important to consider simplicity versus overfitting. Like you see in like the image below of like the 3 graphs, all 3 of these lines like are fits to the data. And you can see that they all do a decent job of like going through the data and like having decent errors. But even just intuitively, we could probably say that the middle graph is the best just because it seems to fit the data the best without overfitting. Like the graph on the right, it might actually have the lowest errors out of all 3, but we wouldn't want to say that this is the model behind the data just because like once we introduce new data that we haven't used before, it's likely to have a lot of errors there. So we want to be really careful with overfitting. And so in general, like there's a lot of techniques to avoid this, such as like regularization, cross-validation, and using different loss models depending on your data. And we won't really like go into that today, but just know that there's like a lot of things to kind of look into more with even like simple things like regression. Yeah, and so usually when using data for like machine learning and stuff like that, you always want to split the data into a training set and a test set. And so this is to make sure that like you don't do stuff like overfitting. Like in the previous image, if we just said that the accuracy of the models was determined with like the same data that we trained on, then obviously like a curve that like just went through every single point would do the best. But we want to be able to generalize this more. So we want to create a test set that was like that the like machine has never seen before, and then use this to test how accurate and like how it would do in like a real world setting. And so basically you just want to use your training set to train the model and then use the test set to actually test the accuracy. Yeah, so in general, you would definitely want to prioritize having high test accuracy rather than high training accuracy. It's really easy to have high training accuracy, but it's really hard to have high test accuracy consistently. Okay, and then there's also like classification. So the idea behind this is that you're given many data points with different class labels, and then you are asked to like predict and classify the new data points. So in general, you would create a decision boundary to split the data, like in the images below. So like the blue dots all belong to one class and the red dots all belong to one class. And like on the XY axes might be like different traits, like it could be like age and like height or color, stuff like that. And so as you can see, like even with this decision boundary we drew, like the data is not perfectly splittable. So this red point, like even like it's technically on the blue side kind of, even though it belongs to the red class. And this happens a lot just because of like errors in taking the data and maybe the variables aren't necessarily perfect. And so for the yellow point, which is like the new data point, we would look at where it falls in relation to the decision boundary. And since it's on the side of like the red class, it would then be classified as a red variable as well. Yeah, and so often data is not easily splittable. So as you can see in like the images below, right, like these are two examples of how you could kind of draw a decision boundary on the same data set. But like the one on the left, it technically has an accuracy of like 100% because every single data point is classified correctly. But even like intuitively, you can tell that this wouldn't be a very good general solution just because like if you introduce another data point, like just because like it's in the small pocket, it's probably their higher chance of being orange than like blue. So this is why like the cluster on or like the decision boundary on the right would definitely be better because it's more general to the data and you could use it for future data as well. And so there are also a lot of other techniques to kind of be more quantitative about this because, you know, we're just kind of looking with our eyes, but you definitely want to be able to quantify how well your data is doing and like how well it is on future things. And so there's also a lot of techniques with that, like decision trees and stuff like that, and like doing random forests. Yeah, so in general, there's a lot of trade-offs to balance feature accuracy. So like the graph on the right definitely has a lower training accuracy, but it'll probably have a higher test accuracy. And like another major topic in machine learning is neural networks. And I feel like this is also a word that's thrown around a lot and people don't necessarily understand it, but basically you have a lot of layers of regression and the most powerful thing about neural networks is that it can model any function. And so the nodes like N1, N2 in the image, these are called perceptrons and they're all kind of interconnected with the kind of component variables like age, salary, education, city. And so these might not have that much meaning to like the situation, but it's just so that each one kind of takes into account every single variable. And so this like, you know, you wouldn't necessarily be able to extract any like sort of pattern or like learn anything about how these variables are interconnected. And so basically how neural networks work there are like kind of hidden layers and activation functions that turn linear weights into non-linear functions. Because basically like you each node has like a linear term, like kind of how we have like, you know, mx plus b. So there's like a linear term and like a bias term. And then like, since they all get kind of linearly like added to each other and affect each other, with like multiple layers, you can actually achieve a lot just with linear weights. Yeah, and we'll see some examples later. Okay, yeah, and then obviously like machine learning has a lot of applications in astronomy, which is like really relevant to you guys, because like there's so much incoming data recently with like, you know, like all the Gaia data and like all the future telescopes that will also collect data in the future. So astronomers need much better tools like machine learning to model and classify data, just because there's so much data now that a lot of advancements in astronomy actually come from better like techniques and algorithms and like on the software side. Yeah, so some kind of examples are like with regression, you know, like inferring stellar parameters from spectra. So like we have some spectra down here, and so some parameters you could extract are like, or it's very easy for the human, like for people trained in spectra to know like what elements are in here, stuff like hydrogen and stuff like that. But since like if your data has a lot of spectra, you definitely want to be able to make a model that can like do the analysis for you instead of doing it yourself. So you might use like machine learning to train your model on like a bunch of images of spectra and tell them like, you know, like this has a lot of hydrogen, like what elements are in them, so that if you give it a new image, like the computer will be able to tell you like what it thinks, which will make everything a lot more faster. Okay, then there's also like detecting supernova. And actually in like Professor Phil Panko's group, like he does a lot of this. And like, so like in the past, because I'm also in the group, like in the past, we would have to go like each day, go through like hundreds of images that were already like pre-filtered, like if they thought there was a supernova. But like at best, there might be one supernova out of like all of the hundreds of images. But like in the past few years, like other groups have made a lot of advancements in like machine learning and being able to accurately like detect supernova just from like going through the images. And so now like we only have to go through maybe like 50 images a day, which is a lot faster. And another like really cool example is like galaxy type classification. So this would be more on the classification side of images. And as you can see, like there's a lot of different types of galaxies. And it might be like really hard for like a person to distinguish all these differences and like be able to do a lot of images. So it definitely helps to have like an algorithm do that. Yeah, and here are some like helpful links in case you guys want to learn more. I definitely recommend maybe taking some more computer science courses like 61A, 61B, or even taking like Data 8. You guys are definitely really prepared for those classes now, like after doing some coding here. And you can even, so like there's this really helpful link that kind of also has a bunch of other links to like resources and videos you can look at. And then also in general, you can always look at the lectures from like Data 8 or like CS61A and stuff like that. Because those lectures are all up and should be like like any Berkeley student should be able to see them. Okay, yeah, so now we can do some demos together. Okay, so this was like a project from this artificial intelligence class I took, and basically it was like we kind of had to make neural networks, although it's kind of hand wavy, but basically like this one was able to do linear, like do regression so that I could model like a sine wave. So it's really cool because in the neural network, it's all just linear weights. So just like mx plus b stuff, but it was able to combine it so that like it becomes a sinusoidal wave. And so we never had to like tell the computer like anything about sinusoidal waves, but it just like from doing a lot of repeated examples and like going through like the losses and trying to get closer to like the actual like curve, it kind of like teaches itself over time. So it's pretty cool. Yeah, so you can see like the loss is already pretty small. Like it's only 0.0, like, you know, 0.05 on average. And like it doesn't quite look right, but like gets closer, which with like the more data it processes, and it's like gone through a lot of iterations, like already 40,000. But yeah, but like by
What?
the end, it'll be pretty cool.
All right, I just want to ask. So, what does loss and processed mean exactly? So
Yeah, so
processed is it's going through.
yeah, process is like how many kind of data things it's going through, because I think it just processes the same data like in many rounds to get closer and closer. And loss is kind of so kind of forget which I think the loss function we used here was seeing like how close the gradients were to the curve of this gradient. But basically in general, just seeing like how close to 0 it can get, because obviously you want a lower loss. Like it's basically saying the number of errors there are. And it's just trying to minimize the error, and that's how it's getting closer and closer to the real thing.
Gotcha, that makes sense. And so, sorry, just another question.
Yeah.
Because I have lots of questions. So, when you say like linear weights and stuff, so I didn't really quite get what you meant by that. So, are you saying like depending on each variable, input variable you have, that's like assigned like like a statistical weight, and it's like changing the weights to like best fit the function or model?
Yeah. So basically, it's kind of like, so there's basically, instead of just having like, so instead of having to make like a really higher order function, like, you know, x cubed plus like x squared and stuff like that, it's a lot of like kind of mx plus b forms, and it's just solving for a lot of m and b parameters, but it's kind of layered in a way that there's just a lot of linear weights. So there's like a lot of parameters that don't really have, you know, like we couldn't really derive them from sine necessarily, but it just kind of adjusts all of them until it like fits the model.
Gotcha.
Yeah.
That's really cool.
That's kind of like the overall idea, yeah. Oh yeah, okay. And I think that just like runs a little bit more, and then it would basically converge. Yeah. And then I have like another example using like digit classification. And so also like an important thing behind these models is that obviously you need like a lot of data for it to run correctly. And so this was used on like a really large data set, like MNIST or something. Yeah, and so this is basically like taking a lot of data samples of like people's handwriting, like different digits from 0 through 9. And it like kind of goes through all of the data sets multiple times to help improve its recognition of like the different numbers. And so if you see like at the bottom, it's like a probability of correct label. So basically for each like image, the computer will like give each digit 0 through 9 like a probability, and it'll just assign whatever the highest probability is like to that digit. So like if you see like the digits on the very right are like have a probability of 1, and those are like the digits that the computer is most confident about. And then you can kind of tell like why the ones on the left side, like in red, they're usually like a little bit more like a little messier, and that's why like their probabilities are lower. And sometimes they're even kind of wrong too, which is why they're in like in red. But yeah. And then over time, you can see the validation accuracy slowly goes up as kind of the computer does more and more training on the data sets. So this is from, oh, yeah.
Sorry, I just had a question. I noticed when you were running that, it said like Epic 1 or Epic 2. So can you run like the same data set or same training set through the model over and over again?
Yeah, so that's
And then, like,
basically what it does. So like right now in the code, it's set to like keep running until the validation accuracy is like above, I think the threshold was around 97 or 98%. And so that's why like Epic 1 is going through like the entire data set, like thousands of images. And then Epic 2 is like doing that again.
Oh, gotcha.
And usually like the
Sorry.
larger data set you have, like the better your results will be, just because you can see so many different scenarios.
Mhm.
Yeah. And if anyone else has any questions, feel free to ask or like type in the chat.
Yeah, sorry I'm asking so many questions. I'm just
Yeah,
so
no, that's
curious.
good. Yeah, so this is from the artificial intelligence class I took. It was CS 188. It was pretty cool. You guys should take it too if you are interested. Okay, and then also in data 100, we did this kind of cool machine learning example where we classified emails as either spam or ham. And so basically like you can kind of imagine like the real world application to that. Like we get so many emails every day, and I think we all kind of know what spam emails look like. Like kind of usually have like really clickbait like subject lines and are always offering like promotions or trying to get you to click on links. So it's a pretty cool project overall. Let me just load it. Okay, and it was pretty cool because this is more on like the data science side of machine learning. So there's like a lot of more like cleaning the data, processing it, and trying to like analyze it. And so like kind of the first step of like this project was to like identify some words or characteristics of spam emails versus your like not spam emails, like ham emails. And so like, why is the kernel not working? Okay. And like I kind of have like the pipeline already set up. Yeah, but so like two words that I like kind of put in to test the frequency of like if they're what the frequency that they appear in like spam emails versus like normal emails. So if we check like the words like free, because I do feel like spam emails are always offering you like something for free, like get an iPad for free or something like that, we can kind of check out the graph that shows like the different frequencies. So from here, you can see like that the word free is like shows up around 0.5 times in like emails, and then versus in normal ham emails, like around 0.3. And then like dear like also kind of like shows up more in spam emails than ham emails. So does anyone have any words they want to try out? We can kind of look together like and identify some words. Yeah, so does anyone have any words that they think would appear in like a spam email, or maybe just like a random word? Either's fine. Okay, so I think some other words, I came up with some words earlier, but I think some other words are like maybe like special, like for a special promotion.
Somebody put
yeah.
one in the chat.
Oh, okay. Sorry, I wasn't looking at the chat. Limited offer, okay. I'll try limited and offer. Okay, yeah, those are offer. See, offer is really good. You can kind of see a big difference between between the spam and the ham. Does anyone else have any words they want to look at? We can also just look at normal words too and see if there's like a difference there. Okay, I'll just try also maybe like be like now. Okay, that's actually pretty similar. Yeah, so basically here we're like kind of doing feature engineering, like kind of selecting features that we think help differentiate between like a spam and a ham email. And so a computer will kind of assign weights to all of these different words. And so it'll like on the training data kind of like get parameters that like get the correct Y label depending on these different labels. And so through this, we'll be able to use this on future emails and like kind of correctly predict what is correct or not. And so a lot that goes into like these kind of data science roles are just figuring out like what features are good and like how you can kind of manipulate the data to find differences. Yeah, and so some other things we might look at are like a lot of spam emails have links. So all of these kind of HTML tags are often really good for that. And then also different things you can look at are like the length of the email or maybe like the words, like how short are the words used? Are there a lot of capital letters? Are there a lot of punctuation? So just stuff like that. Yeah, so now if we kind of go forward with this, we can use the words that we just came up with and try to see how good the model is. So I think with the words that after I spent a while like doing this project a while ago, I had like a training accuracy about like 90 to 93%. And so now we can, and though we only came up with like 6 words and did it kind of quickly, so we can just see how much that is for now. And I also have like a lot of different features, like as you can see here, like seeing if there's a lot of capital letters, seeing like if in the subject there's a lot of capital letters, if this was like a reply or a forwarded email. And so there's a lot of different things you can kind of look at with the data. Yeah, and so you can see like this training accuracy was a lot lower. It was only like 82%. And then on the test set, it was kind of similar actually, is around 81%. And so it's really important that you have like a separate validation accuracy check as well, just so you can see how good it is. Yeah, that's pretty much it for the demo today. Yeah, and overall, this was like a pretty short lecture. So if you guys have any questions you want to ask, totally feel free to ask. But otherwise, you guys can feel free to go.
Can you really quick before they go, can you
Yes.
show them how to access the lectures on the EECS site? Because it might be a little confusing from navigate if you've never seen it before.
Yeah, so if you look at the helpful link slide, if you just click this one for the EECS website, you can see like all of the different CS and EECS courses. So say I was interested in like, I don't think they have data on here, but if just in general, like in Google, you can also just search like Data 8 Berkeley and you'll be able to find it. Yeah, so like say like I was interested in like the introduction to artificial intelligence, I could open this link and it'll take me to the website. And then from here, you can like open up like the PDFs of the lecture, and they also have like links to the recorded lectures as well. So it's pretty cool that basically anyone can access this for free. Yeah, you can even access like all of the homework assignments and projects as well. Okay.